Yeah.
We are Group 2, and we are presenting over the use of electrospun titanium dioxide nanofibers in dye-sensitive solar cells. In the past 2 decades, developing more efficient and cost-effective solar energy cells has been of great interest to the scientific community. Invented in 1988 and further improved in 1991 are dye-sensitive solar cells, which utilize a semiconductor thin film material to generate energy from photons. Although these dye-sensitive solar cells are cost-effective, they are much less efficient than conventional silicon cells. Typically, the structure in these thin films is a nanoparticle array, which has high structural disorder due to the random crystal orientation and also the gaps that you can see between the particles here. And it has a high trap-free diffusion coefficient, but because of the high structural disorder, the electrons take 3-dimensional paths which are not efficient. By using the electrospinning process, we can create a nanofiber matrix which has reduced structural disorder because the electrospin process creates these fibers which have a uniform diameter, crystal size, shape, and orientation. And although it has a lower diffusion coefficient, the lack of disorder in the fibers makes electron transport easier. And the diffusion speeds in the fiber actually approach that of a single crystal material. In one of the experiments we referenced, the highest efficiency found was using 50% nanoparticles and 50% nanofibers for the titanium dioxide material.
This type of solar cell from titanium dioxide is an N-type semiconductor. It's very effective with its surface to volume ratio due to its nanoscale properties and how it is made. The efficiency too can be increased by making it more mesoporous by several processes, and this has greatly increased some of the tests for its efficiencies after it's already so efficient for what it can generate. So some of the test ones have seen go up from 1-2% up to almost 4% increase due to the different mesoporous holes in the structure itself that help generate even more surface area than it already has. The titanium oxide fibers are very efficient in transporting electrons. Their electron transport is very efficient compared to a lot of older solar cells, but they only capture a smaller percentage of the light to actually convert it to electricity. And this makes them very efficient at what they do, but they still don't perform as high as some of the conventional solar cells already. And some of these properties also add to how it is very chemically stable and thermally stable. It doesn't break down, it can withstand so far test environments very well and does not instantly fall apart like some types of nano products do.
These electrospun fibers are electrospun directly onto an FTO conductive glass. This is accomplished by mixing a solution of polyvinyl pyrrolidone, or PVP, acetic acid, titanium tetraisopropoxide. It can also be applied to an acidic kind of gel made up of the same kinds of solutions. Once that is done, it's immersed overnight. That increases the surface area of the titanium oxide nanofibers. Afterwards, a very high voltage is applied to spin the fibers. It's applied to a syringe needle, really. And that forms a jet which deposits the material onto the conductive material as electrospun fibers. In conclusion, this is a very effective and efficient way to create these electrospun fibers. However, there is more research needed to be done to increase that efficiency and to make it a little bit more stable for future use.